Hello everyone. This lecture is going to be about an area in material science and chemistry that's featured a very long use of supervised learning techniques, and is the development of interatomic potentials using machine learning. So interatomic potentials, if you're not familiar with them, are based on routes for solving a very common problem that while you can calculate the properties of a system of atoms using quantum mechanics, it's often too slow. And not only are some methods like density functional theory very slow to even compute the properties of small systems, they have a scaling behavior where here I'm showing the rate at which the computation cost increases with the number of atoms in a system that is quite dramatic. It's a cubed for density functional theory, and it's as high as 10 to the 7 for techniques like coupled cluster. So this means that you're not only have to be prepared to spend a lot of time to run a quantum mechanics calculation, but that you're really only limited to small system sizes because of this scaling. And interatomic potentials come in with the observation that for many kinds of molecular modeling, you don't actually need to know that electrons exist. For things like molecular dynamics, you only need to know the energy of a system at any time, and also the forces acting on each atom, given the positions of all the other atoms. And there are other techniques like Gibbs sampling that require only energies. So if you can create methods that avoid treating electrons, you can not only avoid this big scaling problem, but you can also build models that are drastically cheaper to compute than quantum mechanical methods, and that really scales up the size of problems that you can tackle. Now, as you can imagine, a problem with this degree of impact and easy to understand importance has a number of methods that are available to solve it. And as alluded to by this lecture, there are some where you can use methods that are very recent from the machine learning literature. But really, to give an idea about the spectrum, there exist a number of techniques that vary anywhere on the axis between things that are entirely motivated based on physics and how I relate, say, the environment of an atom to the energy or the forces acting on it, to neural network potentials or other methods where the model forms are not entirely based on physics. So before we get into the machine learned potentials, it's actually worth going in and understanding these interatomic potentials based on physics well. And we'll start off with a very simple one, the Lennard-Jones potentials, which actually were invented about 100 years ago. Now these describe the energy of a system, which we denote V, as a function of the distance between two atoms. And this function has only two terms. There's a 1 over r to the 12 term, which mimics polyrepulsion, which is a force of if I push atoms close enough together that their core electrons interact with each other, I can model that force as a 1 over 12 relationship. And also this dispersive component, which models van der Waals interactions between two valence electron clouds of the atoms, and that we know from physics relates to the energy relates to 1 to the power 6. There are also techniques that are much more modern where you can still see this notion on underlying physics underlying the model form. The Finnis-Sinclair potential from 1983 has a term that corrects these pairwise interactions with something that accounts for how the local density of atoms affects the energy of a system. And we know from theories like tight binding, this should be related to roughly the square root of the density, and that's exactly the term used in this model form. And if you follow that physics out, these pair potentials should be repulsive in nature, and from their original 1983 paper, you can see that they generally adhered to that physical intuition. Now, if we go forward 20 or 30 years from when these potential forms were developed, we can see that the modern incarnations of these forms can deviate quite a bit. There's work from 2019 that changes the functional form of this linear Jones model to make it more computationally efficient to compute and work with embedded atom method / Finnis-Sinclair potentials, where I introduce many more degrees of freedom into the model. As you can see, these pair potentials have much more variation in their curvature than the original models from 1983, which gives them greater prediction accuracy. So even with these simple model forms with clear physics behind them, Pauli repulsion, van der Waals interactions, tight binding, there's room for not only some creativity in how those model forms are actually expressed, but also in the amount of degrees of freedom you introduce into them. And even more modern techniques for fitting interatomic potentials are even more true for this. The MMF 94 potential, which I believe was developed by a drug company, expresses many different physical effects, all within different terms of a model form, and has, I think, maybe close to 100 parameters. And many model forms that, while motivated by physics, are generally empirical. And tools like ReactFF, which can model organic systems and allowing for bond breakages, also have this mix of many different kinds of physics combined together in a complicated model. I think the original React's potential that captured only hydrocarbons had around 100 parameters in it. So very complicated, very difficult to learn all of those parameters, and especially to trace each of them back to the underlying physics. And there's also techniques like MEAM, which came out in the later 80s, that takes the same model form as Finnis-Sinclair potentials, but adds in semi-empirical terms that introduce, say, not just notions of local density, but contributions of the angular terms between those nearby atoms, which again is motivated by physics, but the exact model form here may not be directly traced back to first principles, hence the term semi-empirical. Now these potentials are often fit using a different kind of technique than you may be familiar with the supervised learning models like linear regression and decision trees we've used before. Here, because the model form is fixed, the way these potentials are fit is by guessing many different iterations of these parameters that, and then checking whether, if I ran a simulation with those parameters in the potential, it matches some training data that I've set aside beforehand. And these model forms their dependence on error with parameters can be quite complex, so you have to use techniques like genetic algorithms or simulated annealing that can do global searches, and also often mixing them in with more local things that would say take you from one point in this well here and find the actual minimum of the well in order to be able to determine how to best represent your training data with these parameters. And there are good papers to read about this. This one is from some of my colleagues at Argonne, and you can also find, say, I think it's about a half dozen different codes that will do this kind of optimization of different potential functional forms with global optimization for you. And sort of the last thing I'll note here, which I think really inflects the term semi-empirical and why fully empirical models like neural networks have been used a lot in interatomic potentials, is the idea that's, I think, captured well by Finnis and Sinclair when actually describing their initial potential. Now, while they derived the general form of this model from physics, they do note that the actual form of the model and the physical interpretation of it are, in fact, two different things. That once you start fitting parameters to the data, or fitting parameters to the model, the fact that it was based on physics is only secondary. Or at least that's my personal philosophy, so that's how I interpreted their words from closing on 40 years ago. but it's perhaps a philosophical question best left up to the individual. So let's go on from those simple semi-empirical models where the big focus was talking about how that model form came into play. And now we can branch into techniques that rely more on machine learning. So here I've given an example of 5 of the really major classes of machine learning models that are each differentiated on how they use different kinds of machine learning to learn a functional form. And those can be things like neural networks or kernel learning, which you've seen in some of our earlier lectures, or things that are even based on simple linear or polynomial regression techniques. And so we're going to go through each of these to show how they work. And the one thing that I'll be pointing out through all of these different methods is the way that they handle many body effects. So many body effects in terms of atomic scale physics are the things that drive a lot of complex behavior, like hydrogen bonding within water, or things like bonds having a predefined or preferred binding angle. And the ways that these different interatomic potentials handle many body effects is one way that they're very differentiated from each other, and one of the reasons why many of these methods themselves are so complex. Because we can look at some of the very simple model forms like Finis and Claire. Here they capture the nonlinear behavior of energy versus coordination number, which is indeed a many-body effect. And here, just to clarify, what I'm talking about of nonlinearity of energy with coordination is showing that the binding energy of, say, a dimer, where an atom is surrounded by only one neighbor, is not 1/12 the bonding energy of the same material in a face-centered cubic lattice where it has 12 neighbors. There's some dependence on that bond energy by the number of bonds that that central atom makes, and that gives rise to these many body effects, which you can capture with simple model forms like Finis and Claire. But I'll note that this one here only accounts for coordination number, it doesn't account for bond angles, so you're going to see some of those different ways that we account for both of them within machine learning potentials. And the first of which is one of the earliest that were developed, and this is the so-called high-dimensional neural network potential, which were developed by Baylor and Parinello in 2007, which has 3 main features to note. The first of which is I use as the inputs to my machine learning model these fingerprint or symmetry functions. So what these do is they describe each atom based on the distances between it and the bond angles between its neighbors. So that gives me a single fingerprint which describes a local environment that I pass through a nonlinear neural network. And you'll note that pairwise distances passed through a nonlinear model equals some degree of many-body interaction. So there's one of the check marks that I told you to watch for. And then once I run these fingerprints through the models, that gives me an energy for that specific atom, which I can sum up to describe the energy of an entire system. So let's look into that into a little bit more detail to see how this simple concept can be used to describe complex materials. Now, the first of which is I use a few different varieties of these symmetry functions to describe an atom's environment. I have some which give me a coordination number-like parameter, where I use a radial basis function like a Gaussian, which effectively counts up how many nearest neighbors this atom has. So those are one set of the fingerprints I use to describe. I also have ones which run a filter based on bond distances, where some filters react to, say, atoms that are 3 angstroms away, where others react to those that are 4.5. So it gives me another differentiation of an atomic environment, and I also have ones that depend on bond angles. So there's that other checkbox. Angular terms are captured by having angular symmetry functions. The other bit of complexity you'll see in high-dimensional neural networks is how they account for having more than one atom type, and I do that by having different symmetry functions describing inputs for different types of atoms. So say in water, I would have one set of fingerprints for hydrogen, another set for oxygen. Additionally, oxygen will react to those different environments differently than hydrogen will. So I have separate neural networks to describe each of the different elements. So boom, that gives me the ability to account for differences in atomic environments based on different elements and ways of modeling how those affect different elements. The final bit is how we can handle long-range interactions. So one thing that you can notice about these symmetry functions is they have a distance cutoff. Here it's showing 6 angstroms. The problem is, with some systems, especially ionic solids, a lot of the energy is described by interactions between positively and negatively, or positively and other positively charged atoms. And that interaction energy scales with 1 over r, which means that can actually, in effect, be influenced by atoms that are nearly infinitely apart. So the solution to having this problem of my symmetry functions only react to changes within 6 angstroms, to be able to capture those long-range elements, what I do is I break up my energy into interactions of the atoms based on their charge, which I can explicitly model, and learn the remainder between that with my neural network to capture all those short-range interactions. So these are just the innovations that went into some of these original developments of the Baylor potentials, and there have been a lot of other clever developments along the way of tools like Annie or the maze models that further extend this idea from Baylor and Parlanello to handle different kinds of modeling situations. And a completely different way of taking the same kind of machine learning algorithm and using it to model atomic systems are message passing networks. And a good example for this are the message passing networks of Schutt et al. Called SCHNET, which this, as you may recall from our previous lectures, works using a message and update function. What I do is I take some description of each of my atoms, and you can think of this as a fingerprint describing its local environment. Then I update it based on pairwise distances to each of its neighbors, and then I update it. I update that environment based on those pairwise filters. And the one thing you might wonder is, when I pointed out on that earlier slide that Finis-Sinclair potentials only using pairwise don't get angular terms correctly. The way that works in SCHNET is also an effect of the message passing network. If I look at this cartoon of 2 different systems of 3 atoms, where I have a central atom red with 2 other atoms a fixed distance apart, if I go through one message passing step, I'll notice that my red atom has the same update in features. Same types of atoms at the same distance. But these other 2 atoms are different. Their fingerprints have changed differently because their difference to each other has changed. Now, when I pass my message passing again, even though I've got the same atoms, or atoms at the same distance, their fingerprints are now different because I've updated them, and that gives me the ability to describe atoms that are different based on their environment using only pairwise interactions. So the one last ingredient is how we go from these fingerprints to the actual energy, and here we actually follow the same pattern as that high-dimensional neural network. I pass it through a neural network. That's what these atom-wise layers are doing, and then I sum up all the contributions. So it's a very similar network, in fact, to the high-dimensional neural networks, except that I come up with my own symmetry functions by learning these continuous filters through SCHNET, and I get my angular terms in because of my message passing step. Another very important class of interatomic potential for based on machine learning are the so-called gap potentials, or the Gaussian approximation potentials. The first innovation that enables these is their use of sparse Gaussian processes which Gaussian processes are based on kernel methods, which, as you may have learned from one of our previous lectures, are based on these pairwise kernels, where I have a model form where I can take an atom's local environment, which I'm going to describe with B, and I can predict its energy by summing over its kernel similarity with some set of reference environments multiplied by a coefficient that has to do with each environment. So this gives me a model form that I can gradually increase its complexity, one of the great things about kernel methods, by just increasing the number of basis functions, or the number of environments in. And the interesting thing about sparse Gaussian processes is that this number n is not fixed to the number of training points. In fact, you specify it ahead of time and learn these reference environments simultaneously with fitting the parameters. The other innovation that makes GAP possible is the notion of local environment-based descriptors. So here, it's a simple idea conceptually, but as you'll note, the mathematics are unfamiliar depending on how much kind of computational geometry or even how much quantum mechanics you've done. The idea is I take each atomic environment and as I describe it as kind of a local cloud of nearest neighbor densities, as shown by this cartoon here. Now, what I do second is I take this big 3D function where my function is density as a function of position, and I decompose it into spherical harmonics. So that takes the form of a function that looks like this. Now, spherical harmonics, you may be familiar of from quantum mechanics. Your s orbital is the first spherical harmonic, or with L of 0. Your L of 1 is your p orbitals, L of 2 is your d, and it goes so on from there. So what I do is I create a bunch of these basis functions and I fit the parameters that makes them recreate this kind of little nearest neighbor environment function as closely as possible. I can then create my basis set points, which I'm going to use for my Gaussian processes, by summing over the coefficients that belong to the same L. So here you'll note that my p orbitals have an x, a y, and a z version. And what I'm doing is I'm summing over x, y, and z so that my local environment is no longer, my feature is not dependent on rotation, which gives me some good properties for the potential. Now, the final method we'll talk about today is the linear regression-based method of SNAP. So linear regression fixes or avoids one of the problems that we see with kernel models, and that is that my execution time scales linearly with the number of reference points that I pick. So rather, I can increase or have models that avoid this behavior of complexity by using techniques like linear or polynomial regression. And this is one of the methods that implements this most neatly is called SNAP. Spectral neighbor analysis potentials, that's where the P comes from, and it uses similar kinds of approaches as the GAP we just talked about. Instead of using 3D spherical harmonics, we actually use 4D, so I'm not going to even bother writing them out or showing them as pictures, which give me an ability to have models that are up to 100 times faster than GAP, but with a trade-off in accuracy because I'm going from a complex but expensive calculation to one that's much cheaper, like linear regression. I'll also note that this figure here, where I'm comparing these speedups, was from some work from a rather large team where they worked together to compare all of their methods against each other, which I think is a really beneficial thing to other scientists, having actual experts in the art compare their methods against each other in a way they've deemed fair is incredibly useful for understanding these kinds of trade-offs. The final point to understand about these methods is how they're fit. So Each of these different machine learning models has their own special ways of fitting them, like linear regression you can solve analytically, neural networks you solve with gradient descent. So really the thing that blinds them in how they are fit similarly is the technique of forced sampling. So one of the problems with interatomic potentials is that they have blind spots. And this is an example from a paper I wrote in 2012 where we showed that a potential trained on a solid does something really unphysical in liquids. Some of the elements in this alloy segregate to form little bubbles in the span of only a few picoseconds, which is highly unphysical. Now this potential here was based on a semi-empirical model, so this notion of it having some blind spots is actually to a lesser degree than what we expect for machine learning models, which, given their increased functionality or functional complexity, their lack of as much physical intuition in them, can easily run into these kind of problems. So the way that people often do in practice to fit these machine learning potentials is to run dynamics with their newly created machine learned potential to be able to generate new training data. So this often has a way of elucidating blind spots, just like melting my solid here illustrated on how it did poorly in liquids, something that I originally didn't use in training. And they found that a process where you do this kind of use your potential to go find weird local minima that it may predict to be stable, adding those to the training set and repeating, is one that has been used commonly throughout the community and is described very well from a paper from Bernstein and others of 2 years ago. The other thing to know about fitting machine learning potentials is that there's a number of open source packages that are available nowadays for doing it. So depending on the method, whether you want to use message passing networks or high dimensional neural networks or tools like CUPY, which do kernel-based methods, you can probably find someone's open source package that will help you through that. All right, so that said, the one bit of side lesson I want to introduce with this topic is about how to identify the domain of applicability of a machine learning model. So the domain of applicability is built around the concept of there are certain predictions you can make with a machine learning model that are going to be less reliable than others, say extrapolations versus interpolations, and that there are many different ways of assessing this. So picture this cartoon here, where I've trained a machine learning model on all of the data except what's shown in these grayed out and kind of pinked out regions. So you notice there's a couple different ways I can predict when my model should be unreliable. I can say look at the distance from the nearest training point, and that somewhat correlates with error. I can look at uncertainty predictions from the model, which here are generated by training more than one model at a time. Or I can say not trust any points that are outside of my range of initial training data. So these sort of concepts have a rich variety and also a rich history within the interatomic potential community. There have been many papers that illustrate how if you train an ensemble of models, each on different data, you can make reliable inferences about where a machine learning model should be less trustworthy than others. Or there are techniques where you can say measure the distance from the nearest training point, and studies that show how that is correlated with the error, or tools that are more sophisticated like the extrapolation index, which tells you that if you were to acquire data at this point, by how much would you expect it to influence your model? And that's a technique that works well with linear regression or polynomial regression based techniques, and you can read more about it in this 2017 paper. So that wraps up my lecture for today. There are really three takeaway points that I want you to walk away with. The first of which is that machine learning potentials stand in contrast to the semi-empirical approaches of the past, where in the case of semi-empirical, we fix a model form and then determine the best parameters for it using global optimization. And often that model form is indeed based on some sort of physics instead of empiricism. Machine learning potentials are more based purely on learning the model form with data, so you're fitting parameters with supervised learning rather than global optimization techniques. And within within machine learning potentials, there are many different ways you can approach it that each use different types of learning algorithms, such as neural networks or kernel methods or even linear regression. And that beyond understanding how these machine learning techniques work, one area that you also should become an expert in if you're to use machine learning potentials a lot in your work is how to assess their domain of applicability, and in particular how you can use tools like the distance to a training set or variations within a model's uncertainty to understand where it should be more trustworthy or not. And those are going to be the kind of practical lessons that we'll give in the Jupyter Notebook assignments that go along with this part of the course.